More operations with complex numbers. Now let's discuss multiplying. We have two complex numbers. When we multiply them, we can use the same strategies as we do with multiplying binomials. We can FOIL, first, outer, inner, last. We can distribute, especially if we only have one part in the first complex number. We could use the box method. The only difference between multiplying complex numbers and multiplying polynomials is that when we encounter I squared, we need to replace it with a -1. There should be no powers of I higher than 1 in your final answers. And you'll see why I say that in just a little bit. No higher powers of I other than 1. Let's do some multiplication. And the same idea applies. Pause the video, try it on your own, resume and check, correct your mistakes, do one together and then pause it and then check your mistakes. But the point always is check your understanding. Try it on your own, check your answer. See if it makes sense, find out where it went wrong. It's an important skill for self-learning. In the first problem, 2i times 1/2 minus I. We've got a pure imaginary number in the front, so we're just going to distribute into the parentheses. 2i times 1/2 plus 2i times -I. In the first multiplication, the 2's cancel, and we're left with I. In the second, I times I is I squared, and we have a negative, so this is minus 2I squared. But I'm going to flag it because we cannot keep that I squared there. I minus 2 times -1. The I squared becomes a -1. And then we have I plus 2. -1 times -2 is +2. But we don't get to keep it like that. That's not standard form. A plus BI is standard form. So we just need to switch the order. 2 plus I is our answer. Looking at B, I'm going to use the box method because I love using the box method for multiplying. 5 minus 3i, 1 plus I, and we multiply corresponding sides together for the rectangles. 5 times 1 is 5, 5 times I is 5i, -3i times 1, -3i, and -3i plus I, -3i squared. I'm going to flag that I squared. I have to change it. We can write them all out. 5 minus 3i plus 5i minus 3 I squared is -1, so I'm going to make that change here. One thing to point out in this problem, notice that we have imaginary parts that we can combine. 5 minus 3 plus 5 would give us +2. And then -3 times -1 is +3. Oh, we have real parts that we can combine. 5 plus 3 is 8. We'll do it this way with the colors. Change it up a little bit. And we get 8 plus 2i. That is our answer for part B. Multiplying in C, same idea. We can use a box. And when we multiply it out, I'm going to flag that I squared. And then we'll write all the pieces out inside the box. -6 plus 3i plus 14i minus 7i squared, which is -1. We have imaginary parts we can add together. -7 times -1 is +7. And I have real parts I can add together. -6 plus 7 is 1. 1 plus 17i is our final answer. Again, D, same way. FOIL, distribute, draw a box, whatever multiplication technique you want. And for this one, I'll actually use foiling instead of the box, just to be different. So we multiply first. 3 times 3 is 9. Outer, 3 times negative I is minus 3I. Inner, oh, I could do these in different colors. Let's do that. First, outer, we just did. Inner, and last, I times negative I squared. I'm going to flag the I squared. And we have imaginary parts there. We have real parts. That I squared is going to become real. 9, negative 3I plus 3I, that becomes 0. Negative I squared becomes a minus 1. 9 minus negative 1, 9 plus 1, which is 10. Oh. We multiplied two complex numbers together and got a real number. This happens sometimes. It all depends on the numbers themselves and how those middle terms pan out. But these two are special. Can you see why 3 plus I and 3 minus I are special? The only difference between 3 plus I and 3 minus I is the middle sign. These two are called complex conjugates. Just like the radical conjugates that we talked about previously when we were trying to rationalize the denominator, complex conjugates come into play when we are trying to divide complex numbers, and we really can't, so we multiply by the complex conjugate in a similar way to rationalizing the denominator, so that we can get a whole number denominator instead of a complex denominator. We're going to see complex conjugates again when we study quadratics, because for quadratic equations, complex conjugates come in pairs. We'll talk more about that in the next chapter.